Have you ever felt the ground beneath your feet suddenly start to wiggle and shake? It can be a pretty surprising feeling, can't it? What in the world is going on when that happens? This incredible, powerful, sometimes scary phenomenon is called an earthquake. It's not a monster under the ground or a giant stomping its feet. An earthquake is a completely natural event, a way for our amazing planet Earth to let off a little steam. It's a reminder that the ground we stand on isn't as solid and still as it might seem. These events have been happening for billions of years, long before people were around to feel them, shaping the mountains, valleys we see today. So what exactly is an earthquake? Think of it as a sudden, rapid shaking of the Earth's surface. This shaking is caused by energy moving through the ground in waves, kind of like when you drop a pebble into a calm pond and see ripples spread out. These energy waves travel through the Earth's rock, and when they reach the surface, they make everything shake. Blades of grass, tallest skyscrapers. It's a powerful display of the forces at work deep inside our planet. Understanding these forces is the first step to understanding the science behind these tremendous tremors that can change landscapes in a matter of seconds. To really get what's happening, we need to take a journey to the center of the Earth. Well, not literally, but we can talk about what it's like down there. Our planet isn't just a big ball of rock. It has layers, kind of like a giant jawbreaker, peach. On the outside, we have the crust, which is the thin, rocky layer we all live on. It's thinner under the oceans, thicker under the continents. Beneath the crust is the mantle, a very thick layer of hot, semi-solid rock that flows incredibly slowly, like super thick honey. And at the very center is the core, which is made of super hot metal. These layers are all very different, and the interaction between them is what makes our planet so dynamic and active. The heat from the core warms up the mantle, causing it to churn and move around in slow-motion currents. This movement in the mantle is the engine that drives all the action on the surface, including the big shakes we call earthquakes. It's this incredible heat engine, deep beneath our feet, that sets the stage for the powerful jolts and rumbles we experience on the crust. It's all connected, from the blazing hot center to the ground we walk on every single day. Science is cool, isn't it? Now let's zoom back in on that outer layer, the crust. The Earth's crust isn't one solid piece like an eggshell. Instead, it's broken up into many giant interlocking pieces. These massive slabs of rock are called tectonic plates. Imagine taking the shell of a hard-boiled egg and cracking it all over. The shell would be broken into many different pieces that still fit together. That's a lot like the Earth's crust. These plates are huge, some carrying entire continents, others lying beneath the vast oceans. They float on top of the slowly moving hot mantle layer. These tectonic plates are not standing still. They are constantly on the move, but they move incredibly slowly, about as fast as your fingernails grow. We're talking just a few centimeters per year. You would never feel this movement standing on the ground, but over millions of years, this slow crawl has incredible power. It pushed up the tallest mountain ranges, like the Himalayas, and carved out the deepest ocean trenches. It's a planetary-scale construction project driven by heat deep inside the Earth. So, how do they move? Think about a pot of boiling water. Hot water rises, cools at the top, then sinks back down. A similar process, called convection, happens in the mantle. Hot, gooey mantle rock rises, moves under the plates, then sinks as it cools. This slow circular motion drags the plates along. Some plates are moving toward each other. Some are pulling away from each other. Some are grinding past each other side by side. It's a slow-motion dance on a global scale. This movement is the key to understanding earthquakes. As plates jostle for position, they don't glide smoothly. Their edges are rough and jagged, so they get stuck. As the rest of the plate moves, enormous stress builds at those stuck points, fault lines. All that stress building up along the fault lines has to go somewhere. The rocks can only bend and stretch so far before they reach their breaking point. Imagine bending a plastic ruler. You can bend it a little and it will spring back. But if you bend it too far, it will suddenly snap. That's exactly what happens to the rocks along a fault. When the pressure becomes too great for the rocks to handle, they suddenly break and slip past each other. This sudden, violent release of stored-up energy is what we feel as an earthquake. The longer the plates are stuck, the more energy builds up. and the more powerful the earthquake can be when it finally happens. This release of energy creates seismic waves that radiate out from the point of the slip, which is called the focus. It's like a shock wave traveling through the Earth's crust. There are different kinds of seismic waves. Some travel deep within the Earth. Others travel along the surface. It's these surface waves that cause most of the shaking and damage we experience. They can make the ground roll like an ocean wave. They can shake violently back and forth. The point on the surface directly above the focus is called the epicenter, and this is usually where the shaking is the strongest. There are three main ways that plates interact to cause earthquakes. When two plates collide, one can be forced underneath the other, causing the ground to crumple and creating massive earthquakes and mountain ranges. This is called a convergent boundary. When two plates pull apart, magma from the mantle can rise to fill the gap, creating new crust and causing smaller earthquakes. This is a divergent boundary. When two plates slide horizontally past each other, they can get stuck and then suddenly slip, causing powerful earthquakes along what is called a transform boundary, like the famous San Andreas Fault in California. The magnitude, or strength, of an earthquake is measured on a scale that tells us how much energy was released. A small earthquake might feel like a truck rumbling by your house, barely noticeable. A very large earthquake, however, can release thousands of times more energy and can be felt hundreds of miles away, causing buildings to collapse and the very landscape to change in an instant. Earthquakes happen all over the world, but they are most common along the edges of tectonic plates, in areas sometimes called the Ring of Fire, which encircles the Pacific Ocean. Many people have experienced the Earth's power firsthand. For instance, in 1989, a big earthquake struck near San Francisco, California, during a major baseball game. People watching on TV saw the broadcast suddenly cut out as the stadium shook. The earthquake caused bridges and buildings to collapse. It reminded everyone how important it is to be prepared for the big one that scientists know is coming someday. Another powerful example was the 2011 earthquake off the coast of Japan. This was one of the most powerful earthquakes ever recorded. It was so strong that it not only caused immense shaking on land, but also triggered a massive tsunami, a series of giant ocean waves that caused even more destruction along the coast. It was a devastating event, but it also showed the world how resilient people can be. These real-life events are not just stories. They are powerful lessons in geology and physics happening right before our eyes, showing us the true, raw power of our planet's inner workings. Because earthquakes can happen with very little warning, being prepared is the key to staying safe. People who live in earthquake-prone areas know this well. Families create earthquake kits with essentials like water, food, flashlights, a first aid kit. They also make a plan for where to meet if they get separated. Schools and offices run earthquake drills where everyone practices what to do: drop, cover, and hold on. This means dropping to the ground, taking cover under a sturdy desk or table, and holding on until the shaking stops. So the big question is, can we predict earthquakes? The shocking truth is that right now we can't predict the exact time, place, magnitude. The forces deep within the Earth are just too complex and chaotic. However, that doesn't mean we're completely in the dark. Scientists, called seismologists, can make forecasts. They use historical data, measurements of stress building up along faults, to determine the probability or likelihood that an earthquake of a certain size will happen in a specific area over a period of many years or decades. This helps communities prepare for the future. One of the most exciting areas of earthquake science is the development of early warning systems. These systems don't predict earthquakes before they happen, but they can give people a crucial heads up just moments after a quake has started. The system works by detecting the very first, fastest-moving seismic waves, called P waves, which don't cause much shaking. A network of sensors instantly sends a signal to cities farther away from the epicenter before the slower, more destructive shaking waves, or S waves, arrive. A graphic showing how an earthquake early warning system detects P waves and sends an alert before the S waves arrive. This can provide seconds, or even up to a minute, of warning. What can you do with a few seconds of warning? A lot, actually. These alerts, sent to phones and broadcast on TV and radio, can give people enough time to drop cover and hold on.